Hello all, this video tutorial goes over the answers to quiz 5. So let's just start with question 1, and the question specifies that you must use the reduction potential chart shown during lecture. So I have a picture of the reduction potential chart right here. And first it asks, during anaerobic respiration, many organisms can oxidize NADH with nitrate. So the first step that we need to do with that information is to draw the two redox couples, or the half reactions. So let's think about our electron donor first. So our electron donor is NADH. So we look on the chart under the electron donor section and we find NADH. And we need to first think about, do we need to flip the equation? And the answer is yes. So the electron donor needs to be on the left-hand side of the equation. So let's draw the first half reaction of the electron donor. And the first half reaction is NADH plus a proton yields NAD plus 2 protons plus 2 electrons. Alright, now let's talk about the second half of, or the second half reaction, and that is with nitrate, NO3-, being reduced to nitrite, NO2-. So nitrate is our electron acceptor. So we look, and I specify that in the question, nitrate is our electron acceptor. So we look under our electron acceptor column and we look for nitrate. And here it is right there. And in the question I specify it's reduced to nitrite. So let's make sure that we're grabbing the right equation. And okay, yep, there's nitrite on the other side of the equation. So let's write that down. And keep in mind that that does not need to be flipped because the electron acceptor should also be on the left-hand side of the equation. So nitrate, NO3- plus 2 protons plus 2 electrons yields nitrite plus water. And on this question, even though you didn't need to answer it on the quiz, it asks you to indicate which one represents an electron acceptor being reduced and which one represents an electron donor being oxidized. So let's start with the electron acceptor being reduced. So we already have a pretty good idea because I specified that nitrate is our electron acceptor. So here is our electron acceptor, and it's getting its electrons from NADH. So this is our electron acceptor being reduced. And if I were to put this question on the exam, you would need to just write right next to the equation electron acceptor being reduced. Likewise, this is our electron donor being oxidized. So now that we've done that, let's go ahead and balance the equation. Now this one is a little bit easier than the one that I showed in class because we already have an equal number of electrons. We have 2 electrons here and 2 electrons here. So we don't need to multiply the equation by anything. We can just start canceling. So we can cancel out our electrons and we can cancel out some protons. And then there's nothing left to cancel. So now we can go ahead and write the final equation. So NADH plus a proton plus nitrate yields NAD plus nitrite plus water. So that's our balanced equation, or the complete redox reaction. Now let's do the calculations. So we need to look at the reduction potential of the first one, or the first half reaction, and that's right there, and it's negative 320 millivolts. Now keep in mind that we need to flip that around since we flipped the equation around. So the value would be positive 320 millivolts. Now for the second half, that's right there, and that's 420 millivolts. And since we didn't flip the equation, we don't need to flip the sign. So the standard reduction potential for the complete redox reaction is 740 millivolts. Let's go on to question number 2 now. And the question was, how many turns of the Calvin cycle are required in order to produce one new molecule of glyceraldehyde 3-phosphate? So in order to work out this question, it probably would have been helpful to visualize and draw out the carbons in the Calvin cycle. So let's start doing that. And what we'll do is we'll start out with ribulose 1,5-bisphosphate. And for the purposes of this tutorial, I'm just going to abbreviate that as R1,5, that's a comma there, 1,5-B. So that's ribulose 1,5-bisphosphate. And let's just immediately start drawing our carbons. So ribulose 1,5-bisphosphate has 5 carbons. 1, 2, 3, 4, 5. And through the enzyme Rubisco, a carbon dioxide is added into that. So there's our carbon dioxide, and I'm just going to draw our carbon right there in red. So that's incorporated. And you end up with your unstable 6-carbon intermediate, but then that yields 2 3-phosphoglycerates. And I'm going to abbreviate 3-phosphoglycerates as such. And I'm going to do that to indicate that there are 2 of them. So we're still keeping track of our carbons and where they're coming from. So our first 3-phosphoglycerate has 3 of its carbons originating from ribulose 1,5-bisphosphate, and the other 3-phosphoglycerate has 2 of its carbons originating there, but one of its carbons is from the CO2. Now let's continue on with the pathway. And through a series of steps that we're not going to go through in detail because they're not relevant to this question, you end up with glyceraldehyde 3-phosphate, which I'm going to abbreviate as G3P. Now both of these still each have 3 carbons. And if you recall, one of 2 things can happen to a glyceraldehyde 3-phosphate. It can go off for biosynthesis, or it can be used to regenerate ribulose 1,5-bisphosphate. So the question is, how many turns of the Calvin cycle are required in order to produce one new molecule of glyceraldehyde 3-phosphate? And the answer is 3 turns, because this drawing that I have here represents 1 turn, and in that 1 turn you get 1/3 of a new molecule of glyceraldehyde 3-phosphate. So if we were to do it again, then we'd get a second CO2 that's incorporated, and if we were to go again, we'd get a third CO2 that would be incorporated. So that way you'd get 1 new molecule of glyceraldehyde 3-phosphate. So the correct answer for this question, how many turns of the Calvin cycle are required in order to produce 1 new molecule of glyceraldehyde 3-phosphate? The answer is 3. Next question asks, during respiration, how many molecules of CO2 are released per glucose oxidized? So let's just think about that really quickly. So we're doing respiration. We start out with glucose. So again, let's keep track of our carbons. So here's glucose, and you're doing respiration, so you know that you're going to go through the TCA cycle and through the electron transport chain. So in this particular case, there are CO2s that are released during this cycle, and if you're going through the entirety of respiration starting with glucose, all of your carbons are released as CO2. And since glucose has 6 carbons, that means that 6 molecules of CO2 are released. So the answer for that one is 6. The next question asks, during fermentation, an organism ferments glucose to produce ethanol. How many molecules of CO2 are released per glucose oxidized? So that one's a little bit more complicated to answer. You have to think about the different pathways. So let's again start out with our glucose. And this time we'll explicitly draw our carbons. And glucose has 6 of them. 1, 2, 3, 4, 5, 6. And through glycolysis, you end up with 2 pyruvates. And each of those has 3. Each pyruvate has 3 carbons. Now, if you're going through fermentation to produce ethanol, then you have to think about the pathway that I drew out in class. Remember the one fermentation pathway that I said that you had to know the specifics of? So when you ferment, when you're going through fermentation to produce ethanol via the pathway that we talked about, the first step is the conversion of pyruvate to acetaldehyde, and we're just going to abbreviate that AC. Now, acetaldehyde only has 2 carbons. So in order to, well, where do the carbons go? They're released as CO2. So and during this pathway you go to ethanol. We're just going to abbreviate that ETOH. And each of those also have 2 carbons. So again, the question is, during fermentation, an organism ferments glucose to produce ethanol. How many molecules of CO2 are released per glucose oxidized? And the answer, based on this pathway drawn out, is 2. 2 CO2s are released per glucose oxidized. The final question is, an organism uses the EMP pathway for glycolysis and uses the TCA cycle. For both of those pathways combined, how many net ATPs are generated by substrate level phosphorylation per glucose oxidized? So again, we're talking about per glucose. And again, we need to keep track of our carbons and everything that's going on. So let's start out with glucose, because we're talking glycolysis and then the TCA cycle. So during glycolysis, recall that you have the first part of the pathway, which is the investment part of the pathway. And you end up during that part of the pathway with a glyceraldehyde 3-phosphate. And actually not just one, but you end up with 2 of them. So I'm just going to put a times 2 here. And in order to get to that point, you need to invest ATPs. So here's 2 ATPs, yielding 2 ADPs. Now, here's the energy yielding part of the EMP pathway, and I'm not going to draw out individual steps. Just recall that we end up with pyruvate. And you have 2 steps there where you yield or where you get an ATP. So remember that because we have 2 molecules of glyceraldehyde 3-phosphate, we're going through this twice. And so therefore, you actually get, I'm going to put a multiplier here, times 2, because, like I said, you're going through this twice per molecule of glucose. So now for the EMP pathway, let's add up the number of ATPs generated by substrate level phosphorylation. And that's 1, 2, 1, 2, 3, 4. And then you have to subtract out, 1, 2, 3, 4. And then you have to subtract out 2. So for the EMP part of the pathway, you get a total of 2 ATPs. Now let's think about the TCA part. So here's TCA cycle. And remember that this is running twice because you have 2 pyruvates for every molecule of glucose that you start out with. So remember that during the TCA cycle, there is, for one turn of the TCA cycle, there's 1 ATP that's generated. And since you are running the TCA cycle twice for every glucose, then you can multiply that by 2. So for the TCA cycle, you get another 2 ATPs. So for both of these pathways combined, you get 4 ATPs via substrate level phosphorylation.